Today we're going to continue what we saw on the last lecture on this part, on fitting curves, with the problem of overfitting. So in the last lecture we saw that when we use curves that are too flexible, or in general models that are too powerful for our data, we have this problem of overfitting, of adjusting too much to the training data and then losing the capacity to extrapolate, to predict outside our training data. So today we're going to see how we can solve this problem. One way is to select either the best model or some hyperparameter, some parameter that we can adjust in our model to improve this ability to generalize from the training set to new examples. And in order to do this, we're going to look at some concepts about different errors that we can measure and that we can estimate, and our attempt to estimate the true error of our final hypothesis. So after training our model, we can fit the parameters of our model. We have a specific instance of that model, so an hypothesis, and we can try to estimate how good that hypothesis is. So we're going to see two examples: finding the best degree for a polynomial regression and fine-tuning a kernel regression. I'm going to explain what a kernel regression is, but the idea is similar to what we saw with moving averages and so on. So it's a simple form of regression which has hyperparameters that we can adjust. So in the last lecture we saw that we this idea of beginning with the model. So in the examples I used, it was polynomial curves, and then we find the hypothesis by optimizing the parameters. So we adjust the coefficients of the polynomials in this case in order to minimize the quadratic error between our predictions and the values we have in our data. And we saw that with more powerful models, that is with polynomials of higher degree in this example, we could adjust too much to the data, and so the hypothesis that we obtained, so the actual curves with all the coefficients instantiated, fit too well the training data that it lost the ability to predict correctly the examples outside the training data. So one extreme would be to use a model that is too simple and cannot adjust well to the data. So in this case, if we try to adjust these points fit these points with just a polynomial of degree 1, that is a straight line, we cannot get a very good fit because the line cannot accompany the points. If we increase the degree of the polynomial, then at some stage, in this case degree 3, we can capture the shape of our data. But if we increase too much, then we enter overfitting. This is when we start losing the ability to predict values outside the training data, even though the error for the training set is very low. So let's see these errors in a bit more detail. Our goal in regression is to find these parameters of a function, that is a function with some parameters that we adjust, in a way that when we input x into that function, we can predict the values y that we want to predict. And we saw that we determined the parameters by minimizing the error we were measuring on the training set. But the goal ultimately is to be able to predict any example y from the universe of possible examples. So we don't want to predict examples in our training set, we want to predict new examples from anywhere they may appear. We were measuring the training error because the training error is the error measured in the training set, but the training error is not a good indicator of the error for new examples. And we can see this clearly here. We have a very low training error, but since the training error was obtained after fitting the parameters so that the curve approximates as much as possible the training set, then outside the training set we don't know exactly what the error would be, but it can be very high. So we cannot use the training error as an indicator of the error our final instance of our hypothesis will have when trying to predict new examples, because we are using this training error, this with the computed on the training set, to adjust the parameters. So the question is how we can estimate the performance for new examples in this universe of examples. And the obvious solution is we measure the error outside the training set. So we train with some examples and then we measure the error with other examples that we did not use for training. So let's suppose we do this. We split the data at random in a training set, which are marked here in blue, and a test set in red. So in this case, we fit the curve to the blue points, which are used for training, but then we measure the error outside this set in the test set, in the red points, so that we have an unbiased estimate of the true error. But note that this is an estimate that is computed using a random sample of points. So depending on how the points are split into train and test, we can get slightly different curves and different error estimates. So remember that we are not actually measuring the true error, the error outside the training set. We are taking a sample of points outside the training set and then using that to get an estimate of the true error. However, this is an unbiased estimate. So suppose that the true error is somewhere around here. Sometimes, depending on how the points are drawn, either on the train or the test set, we can get some estimates that are below the true error or above the true error, but on average, if we were to repeat this process many times, it would converge to the actual value of the true error. So we have stochastic estimates, a sample, a random sample of the possible points, but it's unbiased. It can be above the true error, below the true error, but there is no bias there. So this is the concept so far of errors. The training error is the error that we measure in the training data. This is the one we are minimizing when we are adjusting the parameters. The test error is an error measured outside the training data. So in new data points that we did not use for training or for adjusting parameters, and that gives us an estimate, an unbiased estimate of the true error. And then there are these errors that we can conceive but we cannot measure, which is the true error. The true error is the average error for all the universe of possible points. We cannot measure that unless we know all the possible points, and in that case we would not need to fit the curve anyway. And the generalization error we can think of as the difference between the training error and the true error. So this is the error that arises because we are going outside the points that were used to fit the model and trying to predict new values for new data points. Okay, so let's see how we can use these concepts to try to solve the overfitting problem, or at least avoid this problem. As we increase power in our model, the training error will tend to decrease. So this is this example with these points here. And I am plotting the training error in blue for different degrees of the polynomial. So this would be degree 1, a straight line, degree 2, 3, 4, 5, and so on. As I increase the degree of the polynomial, the curve can fit better and better to the points, and so the training error decreases. And this is the error measured on a sample of points that I left out for the test set. So this red line is joining the estimates of the test of the true error that I obtained by measuring the test error for different degrees of the polynomial. So one thing that we can see is that as I increase the degree of the polynomial, these curves tend to diverge. The training error gets lower and lower, but the test error increases a lot. In fact, this is a logarithmic scale, so this can be actually a huge increase depending on the curves that we are using. So in this region here, we say we are underfitting. This is a regime, the kind of model that we are using in this case cannot fit the data very well. So the error occurs mostly because the model cannot provide with an hypothesis that adjusts the data adequately. So you can see that the training error is high, and of course the test error is also high because the model is not fitting correctly. This is what happens in this case. We have a high error because we cannot make the line go close to the point. If we are on the other side, we are overfitting, then the error occurs mostly because the model is fitting too well to the training data and losing the ability to predict outside the training data. So this is what happens, for example, in these cases when we start to get too close to our training data, and then we can get very large errors outside the training set. So overfitting, we can also see it as the problem of increasing the generalization error. That is, we are paying a penalty because the error when we go outside the training set starts to increase. This difference between the training error and the test error. But the most important aspect of this is that what we really want is not the model that gives us the lowest training error, but the model that gives us the lowest error outside the training data. So in this case, it would be here at degree 6, and this would be the best polynomial that we would get here. So let's see how we can do this. We can choose the best model. One way we could do this is to choose the one with the lowest test error. For example, here we have degree 6. This is the curve for degree 6, and it looks very well. So this is the general idea. We're going to choose the curve with the lowest error outside the training set. But if we use the test set for this, we create a new problem. Note that even though each individual estimate here of the true error is unbiased, so it would have a curve somewhere like this. This could be the true error. Each time we measure the true error, we measure the test error to get an estimate of the true error. Sometimes it's below the true error, sometimes it's above. But imagine that we are choosing randomly points for placing on the test set and then measuring the error. And then we do that again and again, and we pick the one, the instance with the lowest error outside the training set. This is what happens if I have a distribution that is like this, but I pick 10 points and then choose the one with the smallest value. And then I repeat and repeat and repeat, and I get this distribution. So if we are throwing the dice, so to speak, several times and picking the smallest value, and then we do that again and again and again, then we will tend towards values that are lower than the average value of the distribution we are picking from, because we are biasing everything through that choice of picking the smallest one out of a sample. So this is a problem if we use this procedure like this. We train different models, we measure the test error, and then we pick the one with the lowest test error. If we do this, when we choose the one with the lowest error, we make it much more likely that we are choosing one that happened to fall below the true error than one that happened to fall above the true error. So this means our estimate is no longer unbiased. It's biased towards underestimating the true error. So we cannot do this like this, because then we lose an unbiased estimate of the true error. And the solution is actually to use 3 data sets. We use the training set to fit the parameters. So this is the blue line here. Then we use a validation set to choose the best hypothesis class, the best model, or the best curve, or the best hyperparameter, anything that we need to choose by looking at the error outside the training set. So if we do this with the validation set, each of these estimates is an unbiased estimate of the true error individually. But when we take this as a whole and pick the smallest one, this process of picking the smallest one makes everything biased towards underestimating the true error. So that's why we retain a test set that we do not use for anything, for any decision, and then we use that to estimate the true error of the final hypothesis. So basically, the training set allows us to fit the parameters of each model or each model with some combination of hyperparameters or something like that. We'll see some examples later, but this is what we are using for fitting the curve. The validation set allows us to choose between different curves, different hyperparameter values, and so on, because we are measuring the error outside the training set. And then when we are satisfied that we have the best possible fit, we use the test set to evaluate the true error in an unbiased manner. Note that we'll see better ways of doing this on the next session, but we're going to start with this one, which is the simplest one and easier to understand. So let's see, as an example, selecting the best degree of the polynomial for this data. We're going to load the data here. This is the polynomial data, and we're going to load this. This is simply a text file separated by a semicolon, and then we are going to load this data and split it into these are 50 points in total. We're going to use 30 for training, 10 for validation, and 10 for testing. So one way we can do this is to create this auxiliary function that receives as input a matrix with our data, and we'll split it into a training set and a test set with this number of points. So one way you can do this is to use the random module from NumPy and then shuffle. For example, we can create a list of indexes and shuffle everything. So this arrange will give us an array from 0 to the number of rows in our matrix. This shape 0 is the number of rows in our matrix. And then when we shuffle this array, we get all the indexes randomly placed along the array. So now we can separate. We'll put on the train set all the rows of our data for which the rank values here is at least as large as these test points value here. So for example, in this case, suppose that we want 20 test points, so the training data will get all those 20 or higher. So from 0 to 19 will be here on the test set. Since these values are all different and are all shuffled at random, we will get a random sample of the rows in our matrix. And then we return the two sub-matrices that we created, the train and the test one. And if we want to use this to split into 3 data sets, we can do it twice. So we get 30 for the training set and the other 20 for this temporary matrix, that then we split 10 each way for the validation and test set. So train is the matrix with 30 points taken at random, and then valid with 10 points taken at random, and test the other 10 points taken at random. And now we can try different polynomial degrees. So we can do a loop here and try different degrees of the polynomial, but we're going to fit the polynomial to the training data, and then we're going to measure the error on the validation data. So for that we can create this auxiliary function that just evaluates the polynomial on the data that we provide and then computes the error as the mean quadratic error between the values in the data and the predictions from the polynomial. But the important part here is this: we are fitting the curve to the training set, but then measuring the error on the validation set. And now we can check if the validation error is below the best one so far. So this best error can start with a very large number just to guarantee that we go into this condition at least once. And then we store the best value, the best coefficients, and the best degree that then we can see at the end. And then finally, so this is using the validation set to select the best set of coefficients, so the best curve and the best degree. And then we take the best one and compute the error on the test set. And this gives us an unbiased estimate of what the true error would be. So remember that because we are using the validation set to choose the best degree and the best curve, then these validation errors will be biased because we are choosing the smallest one. And that's why we need the test error to have an unbiased estimate of the true error of our final curve. So this, in this case, this could be the result. In this case, it was degree 4 with this error here. But note that this estimate depends on the random split. So if the different points here end up in training, in validation or test, I did not represent validation points here, but if the split is different, then the curve will be different and also the measured errors will be different. So you can try this. If you try running this several times, it will give different results. So this gives us an intuition that maybe we should average different runs like this. And this is the basic idea behind cross-validation, which we'll see in the next lecture. So another thing that we can do with this approach of using validation, training and validation, is adjusting hyperparameters. As an example of a model which has these hyperparameters, we are going to use kernel regression with a Gaussian kernel that has this parameter we can adjust. But the general idea of a hyperparameter is a parameter that you can adjust in your model, but is outside the set of parameters that are automatically adjusted during training. So let's see kernel regression with a Gaussian kernel as an example. We're going to use a kernel function to give different weights to the different points in a neighborhood. And a kernel function in this context is simply a function that is not negative, so is 0 or larger. The integral of the function from minus infinity to infinity is 1, so the whole function has a unit area. And the function is symmetrical. That is, the value of the function for minus u is the same as the value for u. These are some examples of kernels that we can use. So we have here a Gaussian kernel, a triangle, a uniform kernel like this, and so on. And the idea of these kernels is to do something that is similar to a weighted moving average, that the one that we saw, but around each point, we're going to use points from our data with different relative weights given by the kernel. So in order to do this, to do kernel regression, we need basically two things. We need a kernel and we need the estimator that will combine the contributions of different points for estimating a value at some specific location. So in this case, we're going to use a Gaussian kernel. This is the formula for the Gaussian curve. And we're going to use the Nader-Watson estimator, which is it's simple to understand, and you can use it when the points are evenly spaced, or you don't care too much about different spacing of the points. So in this case, what this estimator does is to estimate the value at point x, we are going to iterate through all our data and call the kernel, input to the kernel, the difference between each point in our data, the x value of each point in our data, and the value x on which we are trying to estimate the y value. So basically, if we use a kernel like this, Gaussian kernel, this expression here is the output of the kernel. So the further away a point in our data is from the point we are estimating the value, the smaller this value would be. So you can see the curve here, it's larger near 0, so when the difference is very small, but then it falls away on either side. And this is the relative weight we are giving to the y value corresponding to this point, so the point t for each point. And then we are dividing this by the sum of all these terms. So this is a weighted average over all our data set, but the weights are given by, in this case, this Gaussian curve here. So points that are further away weigh less than points that are closer together. There are other estimators. For example, Priestley-Chow uses also this term here so that we can take into account the distance between the x coordinates of the points. This is better when points are unequally spaced. And there are other estimators that you can use. We are not going to worry too much about this. We're going just to use the more intuitive and simpler one, the Nadaraya-Watson estimator. So to implement this, it's simple. We write a function for the Gaussian kernel. This is simply the transcription of this expression into Python. So e raised to minus 1/2 of u squared divided by the square root of 2 pi. And then we can return the computed value. But note that since we are using NumPy functions here, this can be a scalar or it can be a vector. It can be an array with many values, and we compute an array with all the kernels for this vector. And this is useful when we are using then the estimator. So this estimator receives a function for the kernel. This age parameter here that we have, that we can use to adjust the width of the kernel, and this is the one that we're going to optimize, this hyperparameter, and the values of x and y in our data, and the x values for which we want to compute the estimate. So basically what we're going to do is for each point in our data, we're going to compute these sums. So the kernel, using the difference between the point at which we're going to give the estimate and each point in our data, multiplied by the y value, and then divided by the sum of these terms. And this is what we are computing here in order to give this estimate. And since we are using this kernel function that can receive arrays of values, we can do this for an array of x values. So we can obtain a set of estimates for all these lowercase x vector by adding the contributions of all the points in our data. So let's see this graphically because it's easier to understand, and also to understand how the regression depends on this age parameter. So you can see here that we are dividing the distance between each point in our data and the point at which we are computing the estimate by age. If age is very small, then this fraction will be larger, and so this means that the Gaussian curve will fall down faster. If age is large, then the fraction is smaller, and this makes the Gaussian curve fall down slower. So this is what we can see here. If we have a small age value, we give a lot more weight to the points that are nearby and less weight to the points that are far apart. If we have a larger age value, then we give more weight to points that are farther away, and the curve becomes smoother. So we are computing at each point in this blue line the contribution of all the points on our data, and each point is weighted according to that Gaussian kernel and using the age parameter. So for wide age, this becomes very smooth curve. For a small age, then it becomes more intricate, and it accompanies the points better. So now we're going to try to optimize this age, find the best value for this hyperparameter. We can start with a set of values. For example, I'm going from 0.01 to 1 in 40 steps. I can use linspace for this. I get an array of uniformly distributed points between 0.01 and 1. And now I'm going to, for each value here, I'm going to predict the values on the validation set, but using the training set as reference. So basically, I'm using these red dots. Let's say this is a training set, and I'm predicting the values on the coordinates corresponding to the validation set. So this is, I'm giving the Gaussian kernel, the age value that I chose in this step in the loop, the training data, and then I'm asking for the estimates on the validation points. And now I'm going to compute the score, which is the mean quadratic error, and I compute the error by the difference between the y values of the validation set and the predicted values that I used from the kernel regression here. And then I can pick out the best one just by using the smallest value in this list. So this list has all the scores in order. I use argmin from NumPy to get the index of the smallest, of the minimum value in this list. And then I pick the value for age that has the same index. So basically, this is one example of what you get. Note that these plots can vary a lot depending on which points are in the train and which points are in the validation set. But in this case, I have this profile, so the best age would be here, and this is the curve I get with the best age value. Note that if we have a different distribution of train, validation, and test points, we can get a different profile here and find a different value for age. So if you try to replicate these results, you will find that they may change quite a bit. But this happens especially because we have a small data set, and it's on purpose so that you can see these effects. Okay. So this is an important note. All these estimates that we are using, the validation error, the test errors, are computed on a random sample of points. Especially if you have few data points, this can make a big difference from one run to the next. If it's not so bad if you have a large data set, because then statistically it will be unlikely that it would make a big difference. If you have many examples, that you have a good representation of different cases and so on, then in that case you are not as subject to these random factors. So for the exercise that you're going to do, you will use this data on life expectancy and per capita GDP. This is from this site, Index Mundi. It's a table with data for 2003 for 180 countries. So this is the look of the data. When we plot, this is GDP here, and this is life expectancy for these countries. As you can see, this data are a bit messy and all over the place, but the idea is to I'm using these data sets for these examples so that you have it's easy to see the effect of this stochastic sampling when we are estimating these errors. With good data, the effect will not be so obvious, but it's always there, so you need to take it into account. Another thing that this example serves to illustrate is the problem of large differences in magnitude. For example, GDP can go, per capita GDP goes to about 60,000 here in Qatar, and life expectancy ranges from 20 to about 80 something years. So we have values that are very large and very different scales, and this gives us two problems. One is it can result in numerical instability, because let's say you are fitting a polynomial curve and you are raising something to the power of 10 or something like that. If that is 60,000 at the start, you get a huge number, and then when you add smaller numbers, you get rounding errors and so on. So it can give you problems with when fitting the parameters, when fitting the model and such. Another problem is that from data set to data set, if you have widely ranging values, it's very hard to intuitively think about what would be a reasonable quadratic error, what would be reasonable hyperparameters, and so on, because the whole range changes quite a lot. So one thing that we generally do is rescale all these attributes, all the values, and in a regression also the values that we're trying to predict, rescale everything to around 0, 1, something like that. So we'll see more on this later, but for now we're just going to rescale everything to an interval between 0 and 1. So it's all on the same scale and all more reasonable values. So we're going to use the split again, the same function. We're going to load the life expectancy data. In this case, the delimiter is a tab. And then we're going to rescale everything. So we're going to take the maximum of each column. This is the maximum of the data matrix along the rows. X is equal 0. This is the rows, the direction of where the rows increase. And this gives us two values, the maximum of the first column and the maximum of the second column. Using broadcasting, we can now divide all the rows by the corresponding value. So first column by the first value, second column by the second value, so that our data is now rescaled to values between 0 and 1, both in life expectancy and in GDP. Note that this was just a rescaling, so it's like we are changing the units of measurement that we use in order for everything to be in this more reasonable range. In a real-life application, you must retain these scaling factors. So this scale is something that you must keep, because when you are going to predict values for new data points, you have to scale it accordingly. And when you get the prediction from your curve, you need to scale it back to the original units, for example, US dollars or something like that. Otherwise, the result doesn't make sense. After rescaling everything, we can split into training, validation, and test. And now you can experiment finding the best polynomial degree. So use different degrees here. And you'll notice that the results will vary a lot, depending especially on where Qatar is. This outlier here is Qatar. And if Qatar is on the validation set, for example, then you will prefer a curve that doesn't go too far from this. But you'll get widely different curves here, because the training set does not include this point, and so it can go anywhere after the data ends there. If the point Qatar is in the test set, then you won't even have information about this point for validation. So you may choose the best polynomial, maybe something that goes very far from here, and you get a very large test error. If this point is in the training set, then you'll get this effect here, because all the lines will have to cross close to that point when you fit the curves. So this is an example where if you run several times, you can see what the effect is of the points falling in different sets, training, validation, and test. And this is something that if you have good data, you probably don't need to worry too much about this, but you should always keep in mind that this may happen. And you may have to think about how to deal with outliers in your data, with things that are not representative, or when you have very few points and so on. So always be careful to look at your data and see if there may be some problems like this. Also, you're going to fit the best kernel width. This is an example from 0.01 to 0.1, but this is also a bit messy, because depends on which points get left into or are placed in each set. So you may have to experiment a bit with this one, but this would be an example. Note, by the way, that when you use polynomial regression outside the training set, so extrapolating outside the training data, you can get very far away from the points, because you are continuing with the polynomial curve. If you use something like kernel regression, this is similar to a moving average or something like that. So basically you have a constant estimate here based on the last points that you have, because these will have a lot more weight than the others. And so it's a lot more conservative when you go outside your set, but your training set, but it doesn't take into account any trends that you may see. So these are different ways of trying to fit a curve and to compute values that are not in your data. But the general message is that doing interpolation, that is trying to predict values that are inside the range of your training set, is a lot safer than doing extrapolation, that going outside that range. So you can see that when you go outside the range of values you have in the training set, the error can become a lot higher. Okay, so to sum up, we saw these different kinds of error estimates. Training error is actually a measured error on the training set. We are trying to use it as if it would be an estimate of the true error, because we're trying to minimize that, assuming that the best model is the one that minimizes, the best hypothesis, the best instance of the model is the one with the set of parameters that minimize the training set. But because we are minimizing this set, then it becomes very biased, and we cannot really use it reliably at the end of the process to try to estimate the true error. So this is the problem of overfitting. We can get a very low training error, but then have a very large error outside the training set. In order to solve that, we have the test error. The test error is an unbiased estimate of the true error, because we are measuring on a data set that we did not use to decide anything. So we did not affect that measurement by choosing something. In order to choose hyperparameters or the best model or something like that, then we use the validation set, which is a set of points outside the training set, so that each estimate that we do is an unbiased estimate of the true error every time we measure the validation error. However, we know that it will become biased when we measure several times in different conditions and then pick the one with the smallest error, because we are choosing the smallest out of a sample of estimates. We have a biased estimate at the end, and that's why we need the test set to get an unbiased estimate when we finish the process. Also remember that all these estimates are stochastic, so they are affected by the random assignment of points to each of the sets, and the examples I chose for this session are especially chosen to illustrate this in a very obvious way. Of course, in real applications, hopefully you'll have better data and it will not be so obvious, but it's something that always happens and you need to take that into account. So do not expect to get exactly the same results when you run things several times. Okay, so that's it for today. Then we'll have the synchronous session with questions after you try the exercise.